Given that x equals tan squared 4y, where y is between 0 and pi over 8, find dy by dx as a function of x. And we need to leave our answer in that form. So let's start. In order to differentiate this, I'm actually going to rewrite this a little bit. I'm going to rewrite the tan squared 4y in this form. This is exactly the same as this, but it just makes it a little bit clearer as to how the chain rule is going to work, because I've got the tan 4y inside the squared function. So when I differentiate x with respect to y, we're going to differentiate the outside function first, so the squared. So times by 2, take 1 away from the power, and the power is now 1. We would then have to, by the chain rule, multiply this by the derivative of the tan 4y. Tan differentiates to be sec squared. But then I also need to multiply this by the derivative of the inside of that. The derivative of 4y is 4. So that simplifies to give me 8 tan 4y sec squared 4y. Now that's dx by dy. I want dy by dx, so I want the reciprocal. I want 1 over that. Okay, so I've got my gradient function, but I've got my gradient function in terms of y. I want it as a function of x. Now, I know that x is equal to tan squared 4y. So if I square rooted both sides here, I'd find that x, root x would be equal to tan 4y. So in my answer down here, where I've got tan 4y, I could replace that with root x. What about the sec squared? Well, I know that tan squared plus 1 is equal to sec squared. That's one of the trigonometric identities that you need to know. Now the tan squared was x in this question. So actually sec squared 4y could be replaced with x plus 1. So this is going to give me the 1 over 8 times, like I say, the tan 4y gets replaced with the root x, and the sec squared gets replaced with the x plus 1. And all I'm going to do now, to write this in this form, the root x, I can think of that as being x to the power of a half. And then multiplying out those brackets, we'll have x to the power of a half times x is x to the power of 3 over 2. And x to the power of a half times 1 is x to the power of a half. And that's my answer. A is 8, P is 3 over 2, and the Q is a half. Let's have a look at part II now. Right, the volume V of a cube is increasing at a constant rate of 2 centimetres cubed per second. So that's making me think the volume is increasing at a rate, so dV by dt, it's a constant rate, so just equal to 2 centimetres cubed per second. The question's asking me to find the rate at which the length of the edge of the cube is increasing when the volume of the cube is 64. So I want the rate at which the length, so if I say that the length of the cube is x, I want to find dx by dt. Right, connecting the rates of change here then, I can say that this is going to be dx by something times something by dt. Well, I know that dv by dt is 2, so it'd be useful to have that involved, which would make this become a dv as well. So now I'm thinking about how v and x are related to one another. How is the volume of the cube related to the side length x? Well, the volume of a cube is the side length cubed. So dv by dx, differentiating that, I would get 3x squared. But I obviously want the reciprocal of that. I want dx by dv, not dv by dx. So dx by dv would be 1 over 3x squared, multiplied by the dv by dt, which is 2, gives me 2 over 3x squared. Now I want to be able to actually say what the rate is. So I want to find the rate when the volume is 64. So if the volume is 64, I can say that 64 equals x cubed. So x is the cube root of 64, which is 4 at that point. Which, if I substitute that into my equation here, 2 times 3 times 4 squared is 2 over 48, or 1 over 24. And the units would be centimetres per second. The rate of change of the length measured in centimetres, the time measured in seconds, so centimetres per second.